You know, you turn on the tap, water comes out, and you probably don't think twice about it. But have you ever really stopped to consider what it takes to make sure that water is actually safe to drink? Well, behind every single glass is a silent, daily investigation.
I mean, look at it. It's clear. It looks perfectly fine. But that raises a huge question. Does clear equal safe? Not always. In fact, perfectly clear water can be the perfect hiding place for all kinds of invisible dangers, which is exactly why we have to look so much closer.
And that's what we're diving into today, the forensic science of water analysis. Think of us as following a team of public health detectives as they work around the clock, gathering clues and using science to solve the case of your safe drinking water.
So let's start by setting the scene. Why does water that looks totally fine need this kind of intense scrutiny in the first place?
Well, the stakes are incredibly high. Water is absolutely essential for life, we all know that, but it's also one of the most efficient ways for diseases to spread like wildfire. That's why public health labs treat every single water sample like a potential crime scene that has to be thoroughly investigated and cleared before it ever gets to you.
Now, any good detective starts by profiling the suspects. In the world of water analysis, these usual suspects fall into three main categories: physical, chemical, and, of course, microbiological.
First up, we have the physical clues. These are the things you might even notice yourself. A weird taste, a strange smell, maybe the color's a bit off. But labs measure these with incredible precision. Take turbidity, for instance. That's just a fancy word for cloudiness. It has to be below 1 NTU. That's a super sensitive measurement, and a high reading is the first red flag that something's wrong. Next are the chemical traces. And this is where it gets a little scary, because look how tiny these limits are. For lead, the maximum recommended amount is just 0.01 milligrams per liter. That is an insanely small number. These are dangerous, invisible poisons that you absolutely have to find.
And finally, we have the most dangerous suspects of all, the microbiological culprits. We're talking about bacteria and viruses, the invisible enemies that cause serious waterborne diseases. For our water detectives, these guys are public enemy number one.
So what's the acceptable limit for something like coliform bacteria in your drinking water? A little bit, a trace amount? Nope. It's this: 0. It is an absolute, non-negotiable standard. There is zero tolerance. So the million-dollar question is, how on earth do they find them?
To find an enemy you literally can't see, you need a pretty specialized set of forensic tools. So let's head inside the lab and take a look at what they're using to crack the case. It's a fascinating process, really. They can't just put a drop of water under a microscope and hope to spot the bad guys. Instead, they have to create conditions that basically force these hidden microbes to give themselves away. One of the classic methods is the multiple tube fermentation test. Now, it might look a bit complicated, but the idea behind it is actually pretty simple. You give the bacteria some food and see if they show up to eat it. Here's how it works. Scientists take the water sample and put it into this nutrient-rich broth. Then they wait. If coliform bacteria are present, they'll start fermenting the lactose in the broth. As they do that, they produce acid and, this is the key, a little bubble of gas. That gas bubble is the smoking gun. It's the proof. But that classic method takes time. In a potential emergency, detectives need answers fast. And that's where a more modern technique comes in, the membrane filtration method. And this just shows you the key difference, right? Instead of waiting up to 4 days for results, the membrane technique can give a definitive answer in under 24 hours. In a public health crisis, that speed can literally save lives. Okay, so our detectives have found a contaminant. The investigation isn't over, not by a long shot. Now they have to neutralize the threat. It's time to crack the case once and for all.
This all comes down to a really crucial concept: chlorine demand. Think of it this way. Before chlorine can start protecting the water, it first has to fight off all the contaminants that are already in there. The amount of chlorine it takes to win that initial battle is the chlorine demand.
Which brings us to the climax of our whole investigation, and it's beautifully shown right here on this graph. This is the break point. I know, it might look a little intimidating, but it tells the entire story of how water is made safe. So let's follow the journey. In phase A, the first bit of chlorine you add gets used up instantly fighting impurities. In phase B, it starts forming these weaker compounds called combined chlorine. They do some work, but they aren't the goal. Then, at point C, something amazing happens: the break point. You've added enough chlorine to destroy those weaker compounds. And now, in phase D,
Every new drop of chlorine becomes free residual chlorine, and that's the active, protective shield that keeps your water safe all the way to your tap.
And this isn't just theory, these are the real-world tools they use out in the field. Kits like the Horrocks apparatus help operators figure out the exact chlorine demand of the water on site, making sure they add just enough to get past that critical breakpoint and make the water totally safe.
So, after all the tests, all the analysis, all the treatment, what's the verdict? Why does this meticulous, invisible investigation matter so much?
Here are the crucial takeaways. First, clear water isn't always safe water. Second, scientific forensics are absolutely essential for finding those invisible threats. And third, getting the chemistry right is everything. Reaching that breakpoint is the key that unlocks true disinfection and keeps our water supply secure.
Ultimately, it just comes down to this. This entire process isn't just a cool science experiment. It is one of the single most important foundations of modern public health, preventing disease on a massive scale every single day.
So the next time you pour yourself a glass of water, remember the invisible investigation that made it possible. Every glass is a case solved. And it really makes you wonder, doesn't it? What other hidden systems are working right now, all around us, to keep us safe?